What specific problem does the Shared Recurrent Memory Transformer, SRMT, aim to solve in the context of multi-agent pathfinding, MAPF, and why is it crucial to address issues like deadlocks in this area?
The Shared Recurrent Memory Transformer, SRMT, aims to solve the coordination challenges in multi-agent pathfinding, MAPF, by enabling agents to share information through a global workspace, thereby improving their decision-making and avoiding deadlocks. In MAPF, agents operate independently and can only observe their local environment, which often leads to conflicts and deadlocks when multiple agents attempt to navigate through narrow passages or bottlenecks. By utilizing a shared memory mechanism, SRMT allows agents to retain and exchange information over time, facilitating better collective behavior and reducing the likelihood of collisions. Addressing deadlocks is crucial because they can halt progress in pathfinding tasks, preventing agents from reaching their goals efficiently. The ability of SRMT to enhance coordination and mitigate deadlocks is essential for achieving successful outcomes in complex multi-agent environments.
How does the Shared Recurrent Memory Transformer, SRMT, work? Illustrate the methodology step by step, detailing the process of how agents read and write to the shared memory.
The Shared Recurrent Memory Transformer, SRMT, operates by allowing agents to communicate indirectly through a shared memory system, enhancing their coordination in multi-agent pathfinding tasks. Each agent maintains a personal memory vector that is updated at each time step. The process begins with the construction of an input sequence for each agent, which combines the agent's personal memory vector, a historical sequence of observations from the past 8 time steps, and the current observation. This input sequence undergoes a full self-attention mechanism, allowing the agent to process its information effectively. Next, the output from the self-attention layer is passed through a cross-attention layer that integrates the current hidden representations with the shared memory, which consists of a globally accessible sequence of all agents' memory vectors. This interaction enables each agent to incorporate global context into its decision-making process. Finally, the updated personal memory vector is generated for the next time step, and the model output is used to determine the agent's action, thus completing the cycle of reading from and writing to the shared memory.
Can you provide a simple yet illustrative example that demonstrates the inner workings of SRMT, perhaps by walking through a scenario with 2 agents using your method?
In a scenario with 2 agents navigating through a narrow corridor connecting 2 rooms, each agent starts in one room and aims to reach the opposite room. Using the Shared Recurrent Memory Transformer, SRMT, both agents maintain individual memory vectors that are updated at each time step. As they move, they share their memory states through a globally accessible shared memory, allowing them to incorporate information about each other's positions and actions. For instance, if Agent 1 observes that Agent 2 is approaching the corridor, it can retain this information in its memory and decide to wait instead of moving forward, thus avoiding a collision. This coordination, facilitated by shared memory, enables both agents to reach their goals efficiently, demonstrating SRMT's effectiveness in managing interactions in decentralized multi-agent pathfinding tasks.
What are the theoretical or practical benefits of using SRMT compared to existing methods in multi-agent reinforcement learning, MARL, particularly in terms of coordination and generalization?
The Shared Recurrent Memory Transformer, SRMT, offers significant theoretical and practical benefits over existing methods in multi-agent reinforcement learning, MARL, particularly in coordination and generalization. Theoretically, SRMT allows agents to communicate indirectly through a shared memory, enabling them to retain information over time and make informed decisions collectively, which enhances coordination and reduces the likelihood of deadlocks. Practically, SRMT consistently outperforms traditional MARL baselines in complex environments, as evidenced by its superior performance in the bottleneck navigation task and its ability to maintain high cooperative success rates, CSR, even in challenging scenarios with minimal feedback. Furthermore, SRMT demonstrates robust generalization capabilities, effectively scaling to unseen maps and varying corridor lengths without significant performance degradation, unlike many existing methods that struggle with generalization. This combination of enhanced coordination through shared memory and strong generalization abilities positions SRMT as a competitive solution for decentralized multi-agent pathfinding problems.
How was SRMT validated or tested in the experiments? Discuss the experimental design, datasets used, and the metrics employed to evaluate its performance.
SRMT was validated through a series of experiments using the POGEMA framework, focusing on the bottleneck navigation task and lifelong multi-agent pathfinding, LMAPF. The experimental design involved testing SRMT against various baseline models, including Mamba, QPLEX, and others, across different reward functions such as directional, moving negative, and sparse. The datasets consisted of 16 maps with corridor lengths ranging from 3 to 30 cells for the bottleneck task, and 40 maze-like environments of size 65 by 65 for LMAPF, allowing for robust generalization testing. Performance was evaluated using metrics like cooperative success rate, CSR, individual success rate, ISR, and sum of costs, society, which measured the agent's ability to reach their goals, the fraction of agents achieving their goals, and the total time taken respectively. Additionally, SRMT's scalability and performance in unseen environments were assessed, demonstrating its effectiveness in complex multi-agent scenarios.
What significant results were achieved with SRMT in the various benchmarks and tasks described in your paper, including how it compared to other models in those scenarios?
In the benchmarks and tasks described in the paper, the Shared Recurrent Memory Transformer, SRMT, consistently outperformed various reinforcement learning baselines, particularly in the bottleneck navigation task, where it demonstrated superior performance compared to models like Mamba, QPLEX, and others. SRMT excelled under different reward functions, notably achieving high cooperative success rates, CSR, and individual success rates, ISR, even in challenging scenarios like the moving negative and sparse reward settings. Additionally, SRMT maintained competitive performance in environments with corridor lengths up to 1,000 cells, showcasing its scalability and robustness. In the lifelong multi-agent pathfinding, LMAPF setting, SRMT outperformed moral baselines across various maze-like environments, demonstrating its ability to generalize effectively to unseen maps. Furthermore, when integrated with heuristic planning, SRMT floor plans surpassed other methods in highly congested environments, indicating that combining learning-based approaches with planning can enhance performance in complex scenarios.